Is your mind just a very complex computer program, or is it more than this? Let's ask computer science itself. That's exactly what we'll do, and you can verify for yourself her answer by logic or by experiment, even if you're a beginner or an amateur. Imagine an UFO crashing on Earth. Each of its parts is destroyed, except for the brain of an alien robot. Can it be reverse engineered to find its mind? Does this reverse engineering have a unique solution? If consciousness is determined by the physical state of the hardware, it should be possible to reverse engineer the brain of a robot of unknown origin and find a unique mind. But let's start with a much easier problem. Suppose we found not quite a robot brain, but a much simpler alien device. The device has a knob P, a switch Q, a pointer R, each with two possible states. The pointer's state depends on the states of the knob and the switch as shown in this table. So the pointer R is in the state Y if and only if the knob P is in the state B and the switch Q is in the state C. What does this device compute? You can pause the video to think about it. Alice and Bob studied this alien device. Alice thinks it represents an AND logic gate. And if we go through all four possible states of the device, we see that it seems to check well. But Bob thinks it represents a NAND logic gate. And if we check all four possibilities, Bob's interpretation of the device also seems to check well. So who's right, Alice or Bob? Alice and Bob get into a disagreement, each of them convinced to be right. They decide to appeal to Carol's mediation skills. But Carol thinks that the alien device has a different interpretation. So they ask David for help. But David has yet another interpretation. Same for Eve, and Frank, and Grace, and Heidi. So now there are 8 different interpretations. Who's right? You can take a break and think about it. Eventually, they decide to ask Solomon. Alice presents her interpretation. Solomon agrees with her. But when Bob presents his interpretation, Solomon agrees with him too. He also agrees with Carol, and with David, and with Eve, Frank, Grace, and Heidi. Eventually, Solomon agrees with all of them. They object, but we can't all be right. This is right too, Solomon says. All 8 interpretations are correct. This is a representation of the 8 interpretations discovered by our 8 friends. Solomon ponders for a while and proposes the principle of relativity of information and computation. Information and computation are in the eye of the beholder. They're not an objective reality determined by the physical state of the computer, but mere conventions. Relativity of information and computation applies to any computer. A computer is just a machine that changes its state numerous times every second. The present state of its memory cells determines the next state. The alien device is just like the computer, but with only 3 bit cells. One may object. Computers are physical, so computation is objective. Here are 2 examples. 2 push buttons connected in series implement an AND gate. 2 push buttons connected in parallel implement an OR gate. And of course, computers are made of tiny push buttons, the transistors. Except that you can't push down the transistors with your fingers, since they are even smaller than the close add button. That's why your smartphone's processor can contain tens of billions of transistors. But there is no objective reason to interpret on as a 1 rather than as a 0. To ask, is button P down, is just as justified as to ask, is button P up? Okay, make the convention for a bit cell, but then apply it consistently to all other bit cells. There are physically symmetric bit cells for which both conventions look physically the same. There is no objective reason to name one of the states 1 rather than 0. But even if bit cells are not symmetric, there is no objective way to tell which state is 1 and which is 0. Suppose Alice builds a computer in America and Bob builds another one in China without knowing of one another. If they use opposite conventions, can then these computers exchange data? Of course they can. They can use NOT gates. 2 artificial intelligences can communicate even if they are built using different conventions for the bit cells. We use NOT gates to change the convention even in the same circuit. The arithmetic logic unit can add, but we can reinterpret the bits to make it subtract or to do other various logic operations. The same gates are in general used numerous times and interpreted differently during the same computation. That's why any logic circuit can be made using only NAND gates or using only NOR gates. Reinterpretations are omnipresent in computer science. In fact, without them there would be no universal computer. Well, maybe, but a computer reads the data from the memory and writes it in the same way for all bits. Sure, but each of them is interpreted in different ways. Moreover, the same process of the computer can be interpreted in numerous ways simultaneously. Let's look at the idealization of the computer, the Turing machine. It consists of a tape containing symbols from a finite alphabet and a head that reads or writes these symbols. The Turing machine works in discrete steps. At any step, the head can move one cell to the left or move one cell to the right, read the content of the current cell, or write a symbol in the current cell. Each time, the head changes its internal state. When the computation is over, the head halts. Turing machines can simulate other Turing machines, and there are universal Turing machines able to simulate any Turing machine. This is possible only because of the free reinterpretations. Here's an example of input and output of a Turing machine. If it reads 3 ones, a 0 and 2 ones from the tape, it changes the tape so that it contains 5 ones. If it reads a 1, a 0 and 5 ones from the tape, it changes the tape so that it contains 6 ones. If it reads 2 ones, a 0 and 2 ones from the tape, it changes the tape so that it contains 4 ones. Got it? It clearly has two positive integers. The 0 in between behaves like the plus sign. Or maybe it just removes the isolated zeros and we charitably assume that it has any clue of addition. A Turing machine A simulates another Turing machine B if there are some states of A that can be interpreted as the states of B, so that the direct transitions between the states of B correspond to direct or indirect transitions between the states of A. What does this mean? It means that our machine goes through a series of states and we can pick some of these states and pretend that they are the states of another Turing machine. Let me repeat this. A Turing machine simulates another one if you can pick some of its states and pretend that they are the states of the simulated Turing machine. You just have to do it in a way that works for any computation possible of the simulated Turing machine. And there are Turing machines that can simulate any other Turing machine. Let's see some examples. There's a universal Turing machine whose head can be in only 15 different possible internal states and uses only 2 symbols. There is a universal Turing machine with only 3 internal states and 9 symbols. Conway's game of life is a 2-dimensional cellular automaton. Each cell can be in one of 2 states. The current state of the cells determines the next state of the cells by very simple rules. Conway's game of life is also Turing complete. Here's a simpler cellular automaton. It has only a row of cells and each cell can be in one of 2 states. The current state of the cells determines the next state of the cells by very simple rules. If this is the first state, this is the second state, and this is the third state, and this is the fourth state, and so on. This cellular automaton is also Turing complete. Universal Turing machines can be very different in structure and functionality, and yet they can simulate each other. When computers run programs, subprograms, instruction blocks, and so on, parts of their memory and circuits are temporarily reinterpreted to simulate the Turing machines realizing the algorithm. Therefore, their interpretation changes all the time. In computer science, all conventions are allowed and can be used. Without allowing all conventions, there would be no universality, so no programmable computers. The 8 interpretations of the alien device were obtained by reinterpreting each bit independently. But in computer science, we also reinterpret larger groups of bits in any imaginable way. For example, this is the Hamming code for error correction. The value of each bit is encoded as 3 copies. During the transmission, some of the bits may change because of errors. But if at least 2 of them make it to the destination, we can recover the message. So we trust those 2 bits to tell what was the original bit. But this was an easy one. Most error correction codes are more sophisticated. Another example, encryption. The simple XOR cipher works like this. The message in binary is encrypted by XORing each bit with the corresponding bit from the key in binary. The decryption is done in the same way. The encryption methods used in practice are more sophisticated. They reinterpret groups of bits as other groups of bits that seem to have nothing to do with the original ones. And here's the really cool thing. It is possible to compute with encrypted data. The server doesn't need to know what data is processing. You can send it to the server in an encrypted form, and the server computes and returns the output of the computation without even knowing the input or the output. Magic, right? If an artificial intelligence can think, shouldn't it be able to think even if it's encrypted? Especially since all the data being represented according to a convention looks encrypted to you if you don't know the convention. The convention itself is the encryption-decryption key. In conclusion, without secretly changing the interpretation of the bits and the logic gates, programmable computers would be impossible. We would have to buy a different computer for each program, and even so, they would have to be much larger than they currently are. But if it's all just a convention, then why can we use the computers so well? Well, something fixes the computer's interpretation. The hardware and software manufacturers are conspiring to create conventions and to anchor them in the user interface. For example, in the case of the alien device, the labels T and F fix the user interface, enforcing Alice's interpretation of the device as an AND gate. But we've seen 8 different ways to choose the user interface. We create the mind of the computer by pure convention. No, the data structures and the algorithms are objective. We have literally tons of evidence. All these data structures that software developers are using work so well, so they must be real. Right, all of these are real and work as expected, but how much of these structures are intrinsic properties of the computer and how much of them are just our own conventions? Any universal Turing machine can run any of them, even Conway's Game of Life or this simple cellular automaton. These structures aren't written in the computer itself more than personality types and destinies are written in the stars. So whatever the computer does, it's like a skeleton with no flesh. The flesh exists only in our minds. The possible interpretations of the state of the computer as information are not limited to Boolean values like 0 and 1. These are just the low-level interpretations. At the high level, we interpret the states of the computer as containing text, photos, drawings, music, audiobooks, movies, computer games, and so on. The number of possibilities is really endless, but they are all in the user's mind. If the computation done by a robot's brain can become conscious, it should be independent of our conventions. But would there be any computation in the robot's brain without us to make the convention in the first place? How can anything in the robot's brain know of our convention so that it knows what it thinks or even that it exists? If the robot's mind depends on the user's convention, how does the robot get to know our convention? Telepathy? Can a computer even think if no one is around to see it? From computer science, both the theory and practice, it follows that the computer's alleged mind would depend on our conventions. In conclusion, either a computer can't have a mind of its own, or if it has a mind, it has at the same time all minds allowed by all possible conventions. Wait a minute. What if all possible conventions can give rise to sentience? Later, you will see that this would contradict your own observations. This will refute the idea that your own consciousness is just a computation. See you soon.